Do 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 do. Do 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 do. Do 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 do. Do 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 do. All right, so let's start with a fairly easy question. Just what is a pulley? So before we actually look at what they do, let's look at what they are. So in essence, a pulley, you've seen them before. They're basically one circle with a groove cut out of the middle there where the rope or the chain or whatever can go. And all it does is it redirects force. So if you take a look, if this box wants to be lifted up this way, well, instead of just having to apply a force up, you can actually pull on the rope this direction and it will transfer the force. So instead of just pulling it this way, that goes around and it pulls it up. So all a pulley is just a way to redirect a force. Because if you think about it, here you might be leaning back, pulling on it. That's a lot easier than trying to lift up below you. If anyone has ever tried to do a deadlift, it's much easier to pull that same weight down than it would be to do a deadlift and lift it up. So that's basically what a pulley does. It just redirects a force. So let's look at how we might do some force calculations with them. So here's a really simple example with really bad drawing by me. You're welcome. So here is a ceiling with a pulley here. We're going to pretend like that is definitely a pulley. And two boxes are attached by a rope over top of the pulley. One's 8 kilograms, one's 6 kilograms. So based on your intuition, you should probably figure out, hey, what's going to happen here? If we let both of these go, what's going to happen? The 8 kilogram one has more mass than the 6 kilogram one. So guess what? The whole thing's going to go down this way. The 8 kilogram block is going to go down. The 6 kilogram block is going to go up. Okay? All our calculations we're going to ignore any sort of friction that might have to do with the pulley. So we're going to just live in an ideal world where pulleys are frictionless and don't have any effect at all other than redirecting forces. So the only thing we want to know, or that we have to deal with, is the fact that this is 8 kilograms and this is 6 kilograms. So the question that I want to know is, what is the acceleration of the blocks? So just like all of the last questions that we were doing, we need to draw all the forces. So this one's pretty easy. There's only two forces that we have to worry about, and in both cases it's a force of gravity. So here we've got a force of gravity, and here we have a force of gravity. So we know, or we have a pretty good idea, that everything's going to go this way. It's going to go counterclockwise. So we're asking, what is the acceleration in this direction? So why does the pulley matter here? Well, both of these forces are pointed down right now. But if you take a look, what do we say about pulleys? They redirect force. So this force that's pulling down on the 6 kilogram, we could also think of as pulling up on the 8 kilogram. So this force of gravity right here is the same as this one. So I'm going to draw two little lines to signify that these are the same. Let's call this mass 1 and this one mass 2, and then we can call this force of gravity on M2, and this would be the force of gravity on M1. So all we really have to do is look at this one now. These are the two forces that are acting on this. So we know the sum of the forces, and the sum of the forces here, we just have these two, is going to, we know this one's bigger than this one, so we'll have FGM, sorry, I have these backwards, don't I? Oops. Okay, let's call this M2 and this one M1, and we'll fudge it a little bit there, but there we go. So we have, this one's bigger, so this would be force of gravity on mass 2 minus the force of gravity on mass 1, so this subtract this one. And what do we know? Newton's second law tells us that that is going to be equal to, the sum of the forces will be equal to the mass times acceleration. Well, here, it's really the total mass, right? So m1 plus 2 times acceleration. we want to know what acceleration is ultimately. So I can just rearrange this to be acceleration equals fg of m2 minus fg of m1 divided by m1 plus 2. So all I did was divide both sides by m1 plus 2. So now let's actually fill all this stuff in. So the force of gravity is the mass times gravity, right? So m2 times g. Subtract, here it's the same thing except it's m1 times g. And what's m1 plus 2? Well, that's the same thing as saying m1 plus m2. So if we plug everything in here, we should get something out. So m2 is our 8 kilograms times gravity, which is 9.81. Subtract m1, which was 6 times 9.81 again, all divided by m1 plus m2, so 6 plus 8. So let's see, let's plug this all into the calculator. So 8 times 9.81, subtract 6 times 9.81. So I'm going to simplify the top and then simplify the bottom. 19.62 divided by 14. I only did that just to make sure that I don't use my calculator and get an error due to order of operations. And I get 1.4, and this would be meters per second squared. So this mass will accelerate down at 1.4 meters per second squared. This mass will accelerate up at 1.4 meters per second squared. So all this pulley did here was redirect the force of gravity on this one to be pulling up on this block. And we got an acceleration of 1.4 meters per second squared. All right, let's make it slightly different now. This is why we shouldn't dangle objects over the edge of a cliff. So here's an instance where it just so happens that I was thinking about, myself and my kids while I was making up these questions. So this is approximately my mass. This is approximately the mass of one of my kids. And I thought, why is it not a good idea for me to try to dangle my kids over the edge of a cliff? Well, if somehow we were attached by a rope and there was a pulley in between, we'll see exactly why this is not a good idea. Even though my kid has a much smaller mass, about a third of the mass of me, guess what's going to happen? We're both going to come tumbling over the edge. And we're going to do it at a surprising amount of time. So the question here is, again, what is the acceleration? What's the acceleration of these two things going over the edge? They are going to go over. So right now, to make it simple, I've said mu equals 0. So there's no friction. Somehow I'm on the top of a cliff that has no friction between my feet and the cliff. So that's your first dead giveaway that we might go over the edge. So the first thing we always do is we draw in all of our forces. So let's look at mass 1 here. We've got the force of gravity pointed down. We'll just say Fg1. We've got the normal force pointed up. Because I'm not floating and I'm not going through the ground, those would be equal to each other. I don't have any friction, so I don't have any this way. So I think that's all the forces directly on M1. What about on M2? Well, all we've got is the force of gravity on this one. All right, again, what does this pulley do? It redirects force. So this force that's pointed down on this is the same as saying a force pulling to the right on this one. So again, let's start with our formulation of Newton's second law. The sum of the forces is equal to, now I'm going to look at the sum of the forces here pointed in the x direction because I want to know how fast am I going to accelerate towards the edge of the cliff. So the only one really is this Fg2, right? This pulley is redirected. Instead of it pointing down on M2, it's pointed to the right on M1. So the sum of the forces is Fg2, and there's nothing opposing it, so subtract 0, there's no friction, and that equals the mass times acceleration. Well, what's the mass? Again, it's the mass of these two put together. So it's m1 plus 2 times acceleration. So I can rearrange this for, let's just simplify a little bit first. So Fg2 equals m1 plus 2 times a. The force of gravity on 2, what's that? Well, that's the mass of 2 times acceleration due to gravity equals m1 plus m2, m1 plus m2. So rather than just saying m1 plus 2 as a subscript here, I broke it up to be mass 1 plus mass 2 times acceleration. And if we want just acceleration, then we're going to divide by this m1 plus m2, cancel it out. We'll do the same over here. So divided by m1 plus m2. So I have acceleration equals m2 times g divided by m1 plus m2. Now let's fill some stuff in here. So mass 2 is 23 kilograms. Gravity is 9.81 meters per second squared. The mass is added together, so I have 74 plus 23. Let's simplify. So 23 times 9.81 divided by 74 plus 23, that's 97. So divide by 97. This gives me an answer of, with 2 significant digits, 2.3 meters per second squared. So if there's no friction, I'm going to accelerate towards the edge at 2.3 meters per second squared, which for a kid only a third of my weight, that's pretty serious. This is going to end poorly. Let's look at this exact same setup, but instead of there being no friction, we're going to add some friction in here, and we're going to see how this calculation is going to change. So exact same thing here. The only difference is now we have some friction, and the coefficient of friction between me and the ground is 0.26. I must be on ice or something on the top of that cliff. Still dangling my kids over the edge while I'm standing on ice. Still not a good idea. Still don't know why this is happening. Let's stay with that theme of still doing the same stuff over and over again. So let's draw in all the forces first. So we've got the force of gravity on 1. We've got the normal force. Those two should be equal to each other. We now, because we have a coefficient of friction, we know that there's friction opposing the motion. And we have the force of gravity on this guy, which again, this pulley is just going to redirect. Instead of pointing down, we can think of it as pointing to the right. So we're going to do all the same stuff here. So we have the sum of the forces. So here we have pointed to the right, Fg2. But now, opposing it, we have friction. So we're going to subtract friction. That will give us the sum of the forces in the x direction. Equals, and it's the same stuff, the sum of the forces equals mass times acceleration, so m1 plus 2 times acceleration. So let's see if we can plug some stuff in here. So Fg2, that's going to be m2 times g, subtract, how do we calculate friction? It's the fun formula, so F equals mu times n, equals, let's split this up to be m1 plus m2, in brackets, times acceleration. All right, we know m2 and we know g. We know mu. We do not know n right now. So we know from our diagram that n is equal to Fg1. So this, if I just change colors, this is the same as Fg1. And we know how to calculate Fg1. It's going to be g, or m1 times g. So if we just put this in here, we have m2g subtract, don't forget this mu, times n, which is equal to Fg1, which is equal to m1 times g. And over here we have m1 plus m2 all times a. You can do this all in separate steps and then plug it all in together, but I like rearranging and just doing one final calculation. So I do want to find acceleration, so I need to get rid of this m1 plus m2. So I'm going to divide by that, and I'm going to divide this entire side by m1 plus m2. So this is a little bit more complicated looking than when we don't have any friction, which makes sense. Things get more complicated when we have friction. So we have acceleration equals m2g subtract mu times m1g, all divided by m1 plus m2. And everything here I actually know, so I can plug in and solve. So let's get to that. So we have 23 times 9.81, subtract 0.26 times 74 times 9.81. Oh, I ran out of space. Divided by 74 plus 23. Now, let's see if I can use my calculator properly here. So let's simplify the top. 23 times 9.81, subtract 0.26 times 74 times 9.81. And on the top there, I get 36.8856 divided by 97. So just hit divide by 97 equals, and I get 0.38 meters per second squared. And does this answer make sense? Well, yeah, our last question we got 2.3 meters per second squared when there was no friction. If we've got some friction, then that's going to cause us to accelerate slower. So we got 0.38 meters per second squared. That's probably enough time for me to realize, depending on how close to the edge of the cliff I am, probably enough time for me to realize, hey, this isn't going to end well. I probably shouldn't be dangling my kid over the edge of the cliff, and I can all of a sudden start pulling on the rope a little bit more. Hopefully. And we won't go over and end up falling to our doom. So, again, like I said, you can break this all up and do all these individual calculations and then plug them in so that you don't end up with something looking like this, or you can try to work it out like this. I prefer this method. You can do it whichever way you like. Just remember that in its essence, a pulley in these questions is just going to redirect a force. So instead of pointing down, it's going to be pointed to the right on M1. If this was all flipped around, then it would be pulling the other direction. So pulleys just redirect force. So keep that in mind when you're drawing your diagrams and labeling all your forces as you work through numbers 13 through 16 on the friction and forces worksheet. Good luck!